Artificial perfectly black body. Artificial perfectly black body or Ferris black body. A body which can absorb almost all the radiant energy incident upon them is called as perfectly black body. Now suppose this is one plane surface. If I make light to incident at an angle I, which is 30 degree, then reflection will be also at 30 degree, because for light angle of incidence is equals to angle of reflection. Correct?
Also.
Can you tell me what is angle of incidence now? Zero.
Zero.
Correct. So light will get reflected back along the same path. R is also zero.
Yeah.
So if I want that, there should be no ray retracing the path. That means there should be no wave incident at 0 degree. So suppose I make this type of conical projection and allow the beam of light to fall here, or heat radiation to fall here. If I draw here perpendicular, 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 in each cases, you can see I is not 0, because normal will not be perfectly straight because it is inclined. So ray will get reflected back, not on the same path, correct? So perfectly black body means we have to absorb all the heat, no heat should return back. At one place I saw the advertisement, there is 100% privacy because we don't have any common wall. In our flat system, suppose this is my flat, adjacent is another, so this one wall will be common.
Yeah.
So sometimes chances are there sound from one house can reach to the other house. But if this is one block, here there is space kept and then another wall is constructed. So there is no common wall. Or if I place here some soundproof agent, then no sound from one room can enter to the other. So even if somebody is partying with loud sound, he will not get disturbed. So what we take in perfectly black body is double walled, evacuated sphere. So if it is double walled, there is no connection between these two. It is hollow. So it consists of double walled hollow sphere with small opening called as aperture. Again, number. There is black body. That means we are interested in to construct a body which will retain all the heat incident on it. It consists of doubled wall, it consists of doubled wall, hollow sphere with small opening called as aperture. There is small opening here which is called aperture. A conical projection is provided exactly opposite to the aperture. In 10th eye diagram you might have drawn like this. Right? Inner walls are coated with lamp black. Lamp black means, see, in Diwali, if you lit a lamp with wick here and invert it with another lamp. Then that carbon shoot is called lamp black. So it consists of double wall hollow sphere. This is double wall evacuated sphere coated with lamp black. This is conical projection which prevents the heat loss due to reflection along same path. When ray of light is incident, again it consists of double wall evacuated sphere with small opening called as aperture. The small opening is called aperture. Inner walls are coated with lamp black. Conical projection is provided opposite to the aperture. Now working. When heat radiation is incident on conical projection, it undergoes multiple reflection and almost all the radiant energy is retained in the sphere. Due to conical projection, heat loss along the same path is prevented. Thus, it absorbs almost 90 to 95% of radiant energy and behaves like perfectly black body. Okay, understood the meaning?
Yeah, sir.
Yes, sir.
Okay. Chalo, draw the diagram along with me. Double wall, evacuated sphere. Double wall, hollow sphere with small open. This is called as aperture. This is evacuated hollow sphere. Inner walls are provided with conical projection opposite to the aperture. Conical projection. Coated with lamp. Light is incident of conical projection undergoes multiple reflection. Diagram completed then. नहीं, थोड़ा सोचा था दुबई जाके आता हूँ, लेकिन अलाउड नहीं था। 10 घर पे 10 बजे करता हूँ। Yes, completed diagram.
Done, sir.
Write down. Write down. It consists of double-walled hollow sphere. It consists of double-walled hollow sphere. It consists of double-walled hollow sphere with small opening called as aperture. Consists of double-walled hollow sphere with small opening called as aperture. It is provided with conical projection. It is provided with conical projection opposite to the aperture. Opposite to the aperture. It is provided with conical projection opposite to the aperture. The inner surfaces are coated with lamp black. Inner surfaces are coated with lamp black. Then
Done, sir.
actually we have explained work construction, now working here. When radiant energy is incident through aperture on conical projection, then the radiant energy undergoes multiple reflection. Multiple reflection. The conical projection prevents the heat loss due to reflection along same path. Thus, almost 90-95% heat radiations are absorbed. Hence, it behaves like perfectly black body called as Ferris black body. Hence it behaves like perfectly black body, perfectly black body called as Ferris black body, called as Ferris black body. Then
No, sir.
studying state and explain Prevost's theory of heat exchange. State and explain Prevost's theory of heat exchange. See, when we use the word exchange, means it can give, it can take both, not only emitting, not only absorbing. So Prevost suggested that every body can exchange the heat at all temperature except at absolute zero temperature or 0 Kelvin. That means if body is at minus 273, that means it is at 0 Kelvin. Only at this it will not give or take the heat, but at all temperature it will give as well as it will take the heat. So first, what is reverse theory? Then we'll see how we explain. According to Prevost's theory of heat exchange, every body will exchange the heat except at absolute zero temperature. Just write these few lines, then we'll see how it is going to exchange. Means when it will give more, when it will take more, or when it will give same. Every body will exchange the heat at all temperature except at absolute zero temperature.
Done, sir.
Right, next line. The rate of radiations emitted per second depends upon nature of the body, surface area of the body, and temperature of the body. the rate of absorption per second depends upon nature of the body, comma, surface area of body, but temperature of the surroundings. So while radiating, it depends upon its own temperature. While taking from outside, it depends upon temperature of surroundings. Completed?
Yes, sir.
Right. Case 1. Temperature T of body is greater than temperature of surroundings. In bracket you can write T not Kelvin. In this case, rate of radiation is greater than rate of absorption. That means it will give more and take less. Hence, there will be net loss of heat and temperature of body falls. There is net loss of heat and temperature of the body falls. Written, huh?
Done, sir.
Case 2. T less than T. In this case, rate of radiation will be less than rate of absorption. Hence, body will receive heat and will receive net heat, and its temperature will increase. In this case, Rate of radiation is same as rate of absorption. Hence, there is neither loss nor gain. Oh, sorry. In this case, rate of radiation is same as the rate of absorption. Hence, there is neither loss nor gain in the heat. Thus, temperature of body remains constant. This condition is called as thermal equilibrium. So temperature constant is called as thermal equilibrium. If you complete, tell me.
Done, sir.
Very
Then write state the factors on which heat radiated depends. State the factors on which heat radiated depends. So just now we saw it depends upon temperature. More temperature it will give more, less temperature it will take more, same temperature it will give same, it will take same, net is zero. So first point we can write the amount of heat radiated by a body depends upon first case. The absolute temperature of body denoted by capital T. Second, the nature of the body. That is the material and nature of surface. Polished or rough. Material and then nature of the surface, whether it is polished or rough. Surface area of the body denoted by surface area of the body denoted by 4 time. The time. Okay, complete this 3 points first. Fourth point. Time, duration for which the body emits radiation. Denoted by small. Yes, done till this?
Done, sir.
Done, sir.
Yes. Define emissive power. Define emissive power or radiant power. See, generally power means work upon time. Huh? Hello?
Yes, sir.
Power is nothing but work upon time. Correct?
Yeah.
Now we all know work is energy and heat is nothing but energy. So amount of radiant energy emitted per unit time per unit area is called as emissive power or radiant power. So R is Q upon 80. Can you tell me what will be its SI unit? Q is in joule, area is in meter square, time is in second. So
Second.
joule per second meter square, or we can write watt meter raised to -2, because joule per second is also called watt. What will be its dimension? See, what joule is energy. Energy is m1 L2 T minus 2 if you are knowing. Because energy means work, work is force into displacement. Force is m1 L1 T minus 2. Mass into acceleration. Mass दिखा तो m1, acceleration means meter per second square, so L1 T minus 2 into displacement L1. So I have memorized this. m1 L2 T minus 2 is energy. This is L2 T1, L2 for area, T1 for time. So this will become m1 L0
3 minus 3.
T minus 3. Correct. So they can ask you dimension of emissive power, or for 3 marks, define emissive power or radiant power, state its SI unit and write its dimension. Write the heading, then definition I'm dictating. the amount of radiant energy emitted per unit time, the amount of radiant energy emitted per unit time amount of radiant energy emitted per unit time, comma, per unit area is called as emissive power or radiant power. It is given by R equals to
Done, sir.
everybody is done.
Yeah, sir.
Define coefficient of emission or emissivity. Coefficient of emission or emissivity. Which body absorbs maximum? Which body absorbs the heat maximum?
Perfectly black body.
Perfectly black body. One which is good absorber will be good emitter. If it absorbs more, it will give radiate also more. So one who is topper in our class, who absorbs maximum, rest all students will compare themselves with him only. Our black body is good absorber. So I have to compare myself with this good absorber. So rate coefficient of emission is defined as ratio of emissive power R of ordinary body to the emissive power RB of perfectly black body at same temperature. It is given by E equals to R upon RB for perfectly black body heat RB, whatever it has absorbed, that much it will emit. So for perfectly black body, E is equals to 1. For perfect reflector, that means it has not taken anything. Reflector are E equal to C. So these 2 points we have to remember for MCQ. Right. It is defined as, it is defined as the ratio of emissive power of ordinary body, ratio of emissive power of ordinary body R to the perfectly black body RB. It is defined as ratio of emissive power of ordinary body R to the perfectly black body RB. It is given by E equals to capital R upon RB. Then write two lines for perfectly black body. E equal to 1 for perfect reflector. E equal to 0.
Done, sir.
Right. State and proof. State and proof Kirchhoff's law of radiation. Kirchhoff's law of radiation. State and proof Kirchhoff's law of radiation. What is this alphabet in this chapter? Coefficient of absorption,
Yeah.
or it is also called as absorptivity. What is E? Coefficient of emission or emissivity. So when temperature is same of the body and surrounding, then coefficient of absorption and emission are same. Same temperature means thermal equilibrium. Hello?
Yeah, sir.
Now see the statement. For a body emitting and absorbing, because Prevot said every body can radiate as well as absorb. So a body emitting and absorb. Thermal radiations. For a body emitting and absorbing thermal radiations at equilibrium, coefficient of absorption is always equal to the coefficient of emission. That is, therefore, A equals to, this is called Kirchhoff's law. For body emitting and absorbing thermal radiation at equilibrium, coefficient of absorption is always equal to coefficient of emission. Therefore, A equal to E. Right? Till this, then I am proving how it will be A equal to E.
Done, sir.
Just I am proving this, then we'll stop. Tomorrow, this chapter will get over. Oh, sorry, half radiation part will get over. 3 more lecture, KTG part. Today date is 15. Huh? Suppose this is constant temperature enclosure. That means if you give it heat, give this body some heat, it will reject the same heat. So neither it is absorbing nor it is emitting net heat, therefore temperature remains constant. I am showing you two bodies here. One is ordinary body A, other is perfectly black body B, kept in constant temperature enclosure. Kept in constant temperature enclosure. Just draw this diagram. Two bodies A and B. A is ordinary body, B is perfectly black body, kept in constant temperature. Is completed full diagram?
Yes, sir.
अभी थोड़ा रुको, मैं पूरा समझा देता हूँ फिर कॉपी करना, बहुत सिंपल. Consider two bodies, comma, ordinary body A, comma, perfectly black body B, to be kept in constant temperature enclosure. Consider two bodies, ordinary body A, comma, perfectly black body B, to be kept in constant temperature enclosure. Let Q be the amount of radiant energy incident per unit time, comma, per unit area on both the bodies. On both the bodies. That means we are giving same amount of heat to ordinary body as well as perfectly black body. Let R, comma, RB be the emissive powers of ordinary body and perfectly black body respectively. Ordinary body and perfectly black body respectively. Let A, comma, E be the coefficient of absorption, comma, emission respectively. So just general we have written meaning of R, RB, A, E and Q. Please copy till this. Consider two bodies, ordinary body A, perfectly black body B, to be kept in constant temperature enclosure. Let Q be the amount of radiant energy incident per unit time per unit area on both the bodies. Let R, comma, RB be the emissive power of ordinary body and perfectly black body. A and E be the coefficient of absorption and emission respectively. Completed?
Done, sir.
For ordinary body A. Whatever I am writing for A, exactly same I will write for B. The amount of radiant energy incident per unit time, comma, per unit area is Q. Q is the total heat which we have make it to be incident per unit time per unit area on that body A as well as B. The amount of radiant energy absorbed per unit time, comma, per unit area will be. See, Q is incident. Suppose QA absorbs, then this ratio is called coefficient of absorption. So can I write AQ? We gave heat Q per unit time per unit area. It absorbed QA. So QA is nothing but AQ.
Yes.
Sir.
But temperature is kept constant. So heat loss will be same as heat gain. So it has absorbed AQ. Its emissive power we have taken R. So whatever it has absorbed, same it will emit because temperature is kept constant. No?
Sir.
We gave Q, it took AQ. Since temperature is constant, therefore heat absorbed equals to heat emitted. Heat absorbed is AQ, heat emitted per unit time, per unit area we are telling every time is nothing but radiant power R. Write equation 1. Please copy. Just 4 minutes more, we'll be able to complete this part. So next class, radiation is black body radiation, Stephen's law, that will complete, and 3 lectures will be required for KTG part. Completed?
Yeah, sir.
Then same thing write down. The amount of radiant energy incident per unit time, per unit area equal to Q. Amount of radiant energy absorbed per unit area is also Q, because it is black body. Whatever is incident, it will absorb. Then temperature remains constant, heat absorbed equals to heat emitted. Therefore, Q equal to RB, equation 2. Copy till this. So you all are understanding, or I should go more slow?
Understanding.
Okay, any problem comes, tell, then I will go a bit slow.
Yes, sir. No problem.
Take it.
Done, sir.
Done, sir.
Everybody is done? Just 2 lines, then we'll start. Yes, can I clear this?
Yes, sir.
Dividing 1, 5, 2, we get A is equals to AQ upon Q equals to R upon RB. Q cancel. A equals to R upon RB. What is R upon RB? E. Correct now?
Yes, sir.
This proves Kirchhoff's law of radiation. Complete now. This proves Kirchhoff's law of radiation.
Done.
Okay, that's all for today. And